Well, hello, it's time to talk a bit about trigonometry, or the study of triangles. Now, this study of triangles began a long time ago, in the time of the ancient Greeks, and in particular a gentleman called Pythagoras. I'm sure you've heard of him. Pythagoras understood a number of things, and one of them was that the sum, and this is a symbol for sum, it's the Greek capital letter sigma, of the angles of a triangle, or any triangle, equal 180 degrees. He also understood that for a triangle, the square of the hypotenuse equal the sum of the square of the other two sides. So if we call the other two sides O and A, this equation was true. And to illustrate that, to draw you a simple triangle, right angle triangle, and of course this theory applied only to right angle triangles, H being the hypotenuse, being the longest edge of a right angle triangle, calling that side O and that side A, then H squared equals O squared plus A squared, and that's now come to be called Pythagoras' theorem, although it's likely that he picked this up off the Babylonians that he spent some time with when taken captive from Egypt. So though Pythagoras managed to prove that this was true, although it was likely known by the Babylonians already. Okay, now Pythagoras' theorem to one side. The Pythagoras followers were called Pythagoreans, and they formed a religious group who believed that the world could be understood and God could be understood through maths. And as a result, they looked for relationships between the physical world and mathematical entities. And they saw many examples where this was the case, especially in the case of repetitive or harmonic motions between the physical and maths. And in particular, at the heart of a lot of what they saw was geometry, and in particular trigonometry, that particular branch of geometry. Now, as mentioned before, trigonometry is the study of triangles. So let's have a little look at what they found. Now, they discovered that for any right angle triangle, let's draw one here now. It's a symbol for a right angle. The longest edge was always called the hypotenuse, and that name has to do with great tension, and it's likely that it may have been seen that these two other sides were actually part of a bow, possibly, that were tensing a bowstring, called the hypotenuse. And the angles that subtended sides on the triangles were given letter names, and often Greek letter names. Theta is a very popular one. They could have also been called alpha or beta or gamma or delta, any number of other Greek letters, names, and we still use those names today in honor of their origins, their ancient Greek origins. Now, to pick any angle in a triangle other than the right angle, we can name the other sides as opposite relative to this angle that we've chosen, opposite the angle, because that's where it stands, directly opposite, or A for adjacent the particular angle that we've chosen. H, of course, standing for hypotenuse. Well, the Greeks noticed that as the angles changed, the sides changed in fixed relationship to the angles. So the change of sides and angles in a right angle triangle occur in a predictable way. There's a single r there, in a predictable way. You could almost say that they follow a pattern, and that's what these Pythagoreans were interested in, and we are today as well. Now, the relationships came to be given certain names, and these relationships of sides to angles in a right angle triangle were given the Latin names sinus, which later came to be shortened to sine. They were given the name complimenti sinus, or the complement of the sine, and that later came to be called cosine, or just cos for short, and tangere. And tangere is Latin for touch, and we get our word tangent, and that was shortened down to tan. Now, the sine described the relationship between an angle and, so let's call the angle theta, and the opposite side to this angle over or respect to the hypotenuse. So that's a ratio, it's a relationship. The cos of an angle was going to be the relationship between the adjacent side of that angle and the hypotenuse, and the tan of the angle was going to always be the relationship between a particular angle, theta for example, as we've indicated, the opposite side as compared to the adjacent side. Now, those relationships became the standard usage to describe trigonometric properties of triangles. So, okay, how does this affect us, and what's the importance of this? Well, triangles, it appears, can be at the heart of describing a lot of repetitive or harmonic motion. So I'll write that down here now. Repetitive or harmonic motion. What do I mean by that? Well, I mean any kind of repeating regular motion. So an example would be the waves of the sea, it could be the movement of planets, or the orbit of planets. The ancient Greeks understood that. They, many of them were able astronomers, and they knew that the Earth was round and it orbited, or beg your pardon, they thought it was the centre of the universe, and other planets moved around them. It also describes things like the seasons as they come and go, which of course is related to the rotation of the Earth. Now, Pythagoras lived around about 590 or so, or 600 BC. So you're talking a long time ago now, at the time when the Iliad and the Odyssey were being written by Homer, that kind of time period. He was developing and devising and refining his geometry, understanding of the world through geometry. We understand nowadays that these patterns that the Pythagoreans identified are also true in other areas. For example, light. Light has wave properties, repetitive motion properties, as well as particle properties. We think that repetitive motion can also describe the movement of electrons in a conductor under the influence of an AC current. AC meaning alternating current, it drives them backwards and forwards in regular movement. AC current. And also there's an interesting effect which is worth noting called the piezoelectric effect, where tiny crystals will vibrate or oscillate under the influence of an electric current in a very regular fashion, so regular and so precise that we use them in timepieces to create accurate timing, for example in digital watches. So that's just some of the repetitive sort of motions. So how does this relate to a triangle? Well, we could consider, and this is what we'll do now, a triangle, a right angle triangle, placed in the context of a circle. So if we draw ourselves a set of Cartesian coordinates now, and here's the vertical axis, and instead of measuring x and y, let's measure the angle within a right angle triangle, and these trigonometric ratios that we've just spoken, sine, cos and tan. And we'll do this in the context of a unit circle. So if I can hand sketch here as best I can a unit circle for you. May not be as accurate as I'd like. Not too bad. And we'll call it a unit in the sense that it's 1. Here's -1 on the Cartesian coordinate. Actually, we won't even call it -1. Let's start with we'll call it in degrees. -90 degrees, we'll make that 90 degrees. Here 0 degrees, and step out the distances like that. 180 degrees, 270 degrees, 360 degrees. And just for the sake of clarity for later on, I'm going to draw a few dotted lines just to give me a bit of a guideline when I begin to graph some of these trigonometric functions. Now let's start off with sine. So if we graph the angle, and we're talking again just to remind you about a right angle triangle where we have an angle here, theta, and the hypotenuse, and an opposite and an adjacent. So I'm going to draw that right angle triangle here now inside this circle in red. There it is. There's my right angle. This will be the hypotenuse, and it equals 1, unit of 1. And this is the angle theta inside there. Okay. Now, to plot sine theta, I'll take it down a little bit here. When sine, remember it's opposite over hypotenuse, we'll call that O, and there's A. When sine of 0 degrees, what will happen? When theta is 0 degrees, the opposite will be very, very, very small. The adjacent will be 1. Sorry, the opposite over the hypotenuse. The opposite will be very, very small, and the hypotenuse will remain at 1. It has to, as it follows and tracks through this circle. So if I could just draw you a little sample there, it'll be a very tiny little triangle with a very acute theta there. Yep. Okay, and there's your right angle right in the corner there. So opposite will be very small, so it'll be 0, or go close to 0, divided by 1, which is 0. Now sine of 90 degrees well, when theta expands and increases up here to 90 degrees, sine of 90 degrees, the opposite, is going to go very close to 1, and the hypotenuse will remain at 1. So it'll be 1 over 1, which equals 1. So 90 degrees, if we're plotting this, There it is there. It'll be 1. And at 0 degrees, it's 0. Now to get to 180 degrees, we're going to have to swing this radial arc around here, all the way around to minus 90 to get ourselves our 180 degrees. Now, 180 degrees, we're going to, instead of, it would no longer be a right angle triangle if we were trying to measure this arc all the way from here to there. That would no longer be a right angle triangle. So we're going to drop it around and use the complement angle, which is the angle here, and that will in fact produce the same result as the 180 degrees. Don't have time to prove it, but it does. So in this case, here is now the angle theta that we're going to use, and the opposite again is here, and the hypotenuse is there. SCH for hypotenuse. Now, as theta approaches 180 degrees all the way down, this little angle in here is going to go close to 0. So the opposite again is going to be 0 over negative 1. So sine of 180 degrees is going to equal to 0 over negative 1, which is still 0. So we're back down to here. Now if I stretch the angle down here to get close to 270 degrees, we're going to find that sine of 270 degrees is going to be negative 1. Push it to 360 degrees, it'll go to 360. And as a result, we're going to get a shape that looks a little bit like this. It's going to go up here, up to there, and then it's going to come back down through the 180 degrees, drop down low down there, and come back up here, and then we were to continue it on, it would just keep going like that in repetitive motion. And that's called a sine curve, and it's a very familiar shape in science and in maths. Alright, then what happens with the cosine? Well, let's try the cosine in blue. So cos of 0 degrees is going to equal to opposite, adjacent over hypotenuse. And when it's down to 0, the adjacent is always going to be 1, and the hypotenuse is going to be 1 because it stays at 1. So the answer to that is, not 0, but 1. So it starts out here. Now, when cos of 90 degrees is going to equal to, theta pushes up towards 90 degrees, the adjacent is going to go to 0, and the hypotenuse is going to remain at 1. It'll go to 0 down through here. Were we to trace it out, we'd notice 180 degrees it'd go to negative 1, 270 it'd be back to 0, 360 positive 1. And if I had to trace that, I'd look something like this. Down here, down to there, up to negative, to 0, back up there, and so forth. And that's the cosine curve. And you look, it's very similar to the sine curve. In fact, it's identical, except it's just 90 degrees out of phase. What about tan? Well, tan's a bit different. Tan of 0 degrees, again, is opposite over adjacent this time, the relationship between those two sides to the angle. Now at 0 degrees, the opposite is going to be 0, and the adjacent will be 1. So it's 0 over 1, which of course equals 0. So the tan does go to the origin of the graph again. Tan of 90 degrees, what happens there? Well, tan of 90 degrees, the opposite is going to go up to 1, but the adjacent is going to approach 0. So we're going to get something like 1 over a very, very small number, which is really going to be infinity. So at 90 degrees, there's going to be an imaginary line here which can never be reached, called an asymptote, and tan is going to travel up here and approach this asymptote, but never quite reach it, because we can never reach infinity. Were we to go further out to 180 degrees, we would notice that tan will go from another asymptote down here. It would go up into 180 degrees. It would be 0 again, and then it would approach another asymptote here at 270 degrees, like this, and go up again, never quite approach infinity at 270 degrees, and it will continue on like this. So there's a repetitive motion again in the tan, but quite a different sort of repetitive motion to what you would notice. There's been asymptote at negative 90 degrees as well. Quite a different repetitive motion to what you would see with the sine and cos graph, because the hypotenuse is now not involved. Okay, so all well and good. What about, how does all this work? How does it apply? How does it affect life? You know, how can we can use it in real life? Well, I'd like to give you an example with that through a classic case of mathematics done by a gentleman called Eratosthenes. Eratosthenes lived around about 290 or so. It's in the 3rd century BC. So I think he was born about 290 BC. So he was aware of all Pythagoras' material. He was also a librarian of the great library of Alexandria in Egypt, so he had access to a lot of books. Now, Eratosthenes lived in Alexandria, and he was aware of a city a certain distances to the south of him called Cyrene. And Cyrene was around about approximately, by measure, 5,000 stadia. And a stadia was a unit of measure which was the length of a stadium, Greek stadium, from Siam, which is modern day Aswan. I think it was called Siam, spelt like that. He knew that. And there was a well at Siam which at a certain time of the year, when the sun's rays shone, they struck all the way down the bottom of this deep well. And I'll draw a picture of it here now. Eratosthenes was aware of this. So let's say this is the surface of the earth here, and there was a well, deep well, and the sun shone at that well at this certain particular day and struck all the way down to the bottom of the well, the sun's rays. And a little bit to a distance here was Alexandria, and this was, I think let's call it Cyan. This could have been Syene. And the distance between Alexandria and Syene, Eratosthenes knew to be about 5,000 stadia. Like that. Now, knowing and realizing that the sun's rays, the sun was very distant, and its rays would most likely be almost considered to be running parallel, Eratosthenes erected a perpendicular stick, or had access to a monument which was perpendicular, and he noticed when the sun rays struck, these parallel rays, almost parallel, coming from the distant sun, came down here, struck the stick at the same time of year as they were coming directly into the bottom of this well at Siam, that there was a small angular difference here, and that angle was 7.2 degrees. So those same parallel rays, or considered parallel rays, here in Siam showed no difference, struck all the way to the bottom of the well, and here instead at Alexandria they showed a difference of 7.2 degrees. Well, considering that the centre of the earth, let's just push it down to here, and realizing of course that if he had two arrows, two parallel, and I'll change colour here now, two parallel lines represented by the sun's rays, one line of these sun's rays would go parallel right into the centre of the earth, the one at Cyan, because the sun was directly above. But on this side here, at Alexandria, the sun's rays would pass some distance from the centre of the earth, in fact 5,000 stadia from the centre of the earth. And this perpendicular stick, which had been erected, if we were to trace a line straight through the middle of it, it too would go through the centre of the earth. Now, knowing basic geometry, if we have two parallel lines, we can use this angle here called an included angle. So the angle here at 7.2 degrees would also be the same as the angle here, 7.2 degrees. Eratosthenes knew his geometry well, and he was aware of this fact. So with these two angles, he could then do two things. Firstly, he knew that the sun, sitting directly above the top of this particular well, he knew the distance from Alexandria, and although the curvature of the earth would have been very slight, it could be ignored. He could construct a right angle triangle all the way from the sun to Cyan, across to Alexandria and back again, knowing that this angle at the top here was 7.2 degrees. Now, using basic trigonometry ratios, he knew the tan of 7.2 degrees was equal to the 5,000 stadia over the distance of the Earth to the Sun. Let's call it delta. Therefore, he could say the delta was equal to 5,000 stadia divided by tan of 7.2, which he could work out. And it turned out that it was quite accurate, that measurement of the Earth and the Sun. So that's the first thing. So that's the distance of the Earth from the Sun. Not bad for a Greek chap without a calculator. The next thing he was aware of, and just dropping this down a little bit here to finish it off, was that in calculating this distance, he knew the 5,000, he knew this angle down here which we've just described, which is an included angle from these assumed parallel sun rays, which was accurate, that assumption. So he could then construct another right angle triangle. Well, no, he didn't even need to construct a right angle triangle here. He knew that 7.2 degrees was a fraction of the total of the Earth's circumference, which, if you placed it as a cross section, would have been a circle with 360 degrees. One divided the other. He knew that he had 1/50th of the Earth's circumference was the equivalent approximately of 5,000 stadia. So let's call this the diameter, not the diameter, the circumference of the Earth. Call it CE. So therefore, the circumference of the Earth was equal to 50 times 5,000 stadia, which was approximately 250,000 stadia. And taking a stadia, I think it was, there was a Greek measurement, Egyptian measurement, it came up to whatever it was. It was quite an accurate measurement. It was around about 1.6% accurate. Oh, it was within 1.6% of accuracy of the actual measurement that we've calculated in modern times. So I guess then you'd say it would be, rather than 1.6% accuracy, you could say that it would be 90 98.4% accurate. That's not bad for a gentleman, using basic trigonometry relationships and some hand calculating, probably on a clay tablet or maybe some papyrus. I'll leave you with that, and just to see a little glimpse of the power of trigonometry and its uses. Bye.